So I'd like to introduce, without further ado, Dr. Jim White, who is at the University of Colorado. Jim has given many presentations here at the Glenn Gerberg Weather and Climate Summit. Everybody has enjoyed them. We always put our presentations on the YouTube page, so those of you watching online can access these presentations at any time. We'll probably have them up by midweek next week. We take them back to Storm Center, we edit them, make sure that they're nice and tight, and we don't cut them at all. We put the entire presentation on the site for you to reference. So Jim, welcome, and thanks very much. Look forward to your presentation.
Thank you, Dave. I've already lost the clicker. So
oh, there it is.
Okay. All right. That started poorly. Laser be earlier.
Right. Okay, that started poorly. All right. So I'm going to blast. What was that? Bingo. For those of you watching online, they handed out a presentation bingo card here, so which I haven't looked at, but it's they're already yelling bingo. So I've got a number of slides I'd like to get through and leave time for conversation afterwards. This is obviously not a topic that anybody cares about, so we'll just blast through it. All right. So I'm going to talk about physics, ethics, and communication, and it's fairly broadly written. I'd like to start with this slide for a couple of reasons. One is it has Typhoon Haiyan on it, which was one of the larger, might have been the largest typhoon or hurricane in the Pacific. The scale of this is just remarkable. If you look at the scale of this thing, it is about as big as this continent, and that continent is, of course, India, which gives you an idea of just how powerful nature is. You also see on here all of these lights. It is curious. If you look back at some of the earliest satellite photographs of the Earth, the pictures of the Earth, the number of lights, much less. And particularly in areas like this, in China and India, these areas have really increased over time. And this is all, of course, electrical lights driven almost 85% on average by coal, oil, and natural gas, which produces carbon dioxide, which leads to the kind of climate changes that we're seeing today. So setting the stage, on this planet, human beings are the major agent of change. This is an important concept that sometimes people miss. I get frequently, and you probably do, the question, how can something as insignificant as human beings change something as large as the planet? And this picture helps understand the answer to that. But also, just some little metrics here you can use. We move 10 times more dirt than all natural erosive processes, and that's the tectonic cycle. That's how our planet functions. Mountains are raised up, they're eroded down. Mountains are raised up, they're eroded down, and that happens over millions of years. We stepped into this process when we started digging big holes in the ground, particularly for removing minerals and coal mining in particular. But we move 10 times more dirt than all natural erosive processes. We exist on this planet because of nitrogen fertilizer. We exist because of plants. Plants photosynthesize, they make sugars that we eat. They produce oxygen as a byproduct, which is necessary for us as oxygen-breathing creatures. So we live symbiotically with plants. Photosynthesis is essential for us to survive. Photosynthesis doesn't exist without sunlight, CO2, water, and nutrients. And there are a couple of big nutrients that plants need. One of them is nitrogen. Phosphorus is eroded out of the ground as plants get it up through their roots. It's water soluble. Nitrogen is mostly in the atmosphere as N2. So if it wasn't for bacteria taking nitrogen out of the atmosphere and making it into nitrate and ammonia, we wouldn't be here. So we exist because of those types of bacteria that take nitrogen out of the atmosphere and as a byproduct leave behind ammonia and nitrate, which are the water-soluble forms of nitrogen. We got involved in making nitrogen fertilizer, nitrate and ammonia, in the 1930s, and in basically one generation. Went from not being involved at all in one of the key cycles, the nitrogen cycle on the planet, to the point now where we make as much nitrogen fertilizer as all of the bacteria on land, which is pretty darn impressive. Right? So I'm going to skip sulfate here, but we'll move on. Now, we did this by two mechanisms. One is there's a lot of us. Exponentials are really powerful, dangerous, exciting things. We went from about 1 billion people in 1800. It took us about 123 years to get to the next billion, about 33 years to get to the next one, and then after that, it really just shot up. So in a matter of 10 to 15 years, we added 1 billion people to the planet. You can sort of pick your birth date here and see how many people were on the planet when you were born. For me, it's less than 3 billion people on the planet, and now we're well over 7 billion people. So in my lifetime alone, we've added 4 billion people to the planet. You are here and you're going up. The pace of change is slowed down. The demographers tell us that somewhere between 10 and 15 billion, if we just continue, business as usual is where we will be. We can get into long discussions about this, but already folks are calculating, well, how much food do you need? How much fresh water do you need? How much resources do you need to sustain 7 billion people? And the answer is we might need another planet or two to do that. And so you can imagine if you get up to the 15 billion range, what kind of challenge we have for the future. The other reason why things have changed rapidly is because the amount of materials that we need for modern lifestyles have increased. And the number of people who have modern lifestyles have increased. So this is just energy. It's in per capita kilogram of oil. But you see that the world is very, very different. In the lower income world, you don't need much energy, and that's because they're pretty much living a subsistence lifestyle. You get up into the middle income areas, and then you get into the high income areas, you see how much additional energy is required. Now, I could have plotted food calories, I could have plotted nitrogen fertilizer, I could have plotted any number of things that we need for a modern lifestyle, and they all scale roughly the same. Low income is somewhere around 3 to 5 times less than middle income, and 10 times less frequently than high income. So for example, India is uses 5 times less energy than Denmark. And Denmark's European countries are about twice as efficient as we are in terms of utilizing resources. And this is as China industrializes, as India industrializes, as countries go from poor to middle and develop a middle class, the amount of materials that they need increases. And not just by a factor of, for example, population goes up by 1 or 2% maximum each year. These are things that go up by 100%, 200%, 300% in a relatively short period of time. And that's really what has crept up on us and changed the landscape over the last 30, 40, 50 years. That has really changed the amount of material, the amount of energy we need, the amount of food we need, the amount of fresh water we need, et cetera. And it's really ultimately the challenge of sustainability. Leads to what I call the nasty dilemma. I've taught a course on energy and the environment for almost 30 years at the University of Colorado, and I've asked my students every year, do they want other people to have the same lifestyle that they have? In other words, would you like the folks in China or India to have the same lifestyle you have? And the answer has historically been yes, although over the last 5 years or so, people sort of stop for a moment and go, well, is that possible? And that's a really interesting change in the sociological landscape, if you will, of how people view the rest of the planet. We can talk about that later. The world's definitely changed. CO2 emissions, it used to be the US and Europe were the top 2 emitters. And so CO2 emissions are a proxy for how much energy you're using. And up until the mid-1980s, 1990s, we were the main show in town. For those of us who have been around for a while, we know that it used to be the discussion about economics was about a handful of countries really driving the show. That changed. China went from really low on this scale to China sort of turned loose around 2000 economically, and the amount of energy that they began to consume shot up. India is poised to do the same thing. If you look at the history of development of humans on the planet, it's episodic. In the mid-1800s to late 1800s, many of the countries that are industrialized now went through an industrial revolution. Now we're going through a second industrial revolution. And really, it's Africa that's left behind now. And eventually, one hopes, or we don't know, they'll go through an industrial revolution as well. So of that 7 billion people, about 5 billion live reasonably well, and about 2 billion live pretty miserably. All basic energy needs have environmental impacts. So one of the things that we cannot get around is the fact that we're going to have a footprint on the planet. If you need energy, you need food, you need water, you need shelter, you're going to have a footprint on the planet. This is another question I get asked all the time is, can we live in a way that we don't impact the planet? And the answer is no. If we're going to have 7 billion or even 5 billion, and we're going to live the way we do, we're going to have to deal with that. Arguing about how we manage those impacts is nothing new. I take my classes through this exercise of let's talk about tetraethyl lead. So tetraethyl lead used to be an addition to gasoline to keep your engine from knocking. It was added in the 1920s. Probably within 5 years of lead being added to gasoline, doctors were saying this is a dumb idea because what you're doing is spewing lead, particularly in inner cities. Lead, we knew at the time, was a retarded development among children and led to lower brain development. It leads to lower IQ scores. There's a whole bunch of reasons why children should not be exposed to lead. Frequently we hear that, don't eat lead paint chips. But lead in gasoline was spread all over inner cities for many, many years. We argued about that for a long time, even though the doctors were telling us, no, this is a bad idea. It took 40 years or more to get lead out of gasoline. The same story can be told about mercury. The same story can be told about dry cleaning fluid, perchloroethylene. The same story could be told about cigarettes. It seems to take us about 40 or 50 years from when we know this is a bad idea to actually doing something about it. And that's a curious thing that you can think about, you can talk about. Sociologists look at this. And climate change is really no different. We knew 40, 50 years ago that this was not a good idea to be adding greenhouse gases to the atmosphere at the level we are, and we still argue about this. By the way, if you're tired of having arguments during family gatherings about climate change, this is a really good argument starter down here. This is the plot of lead exposure and violent crime. So violent crime in the United States has been going down. And a lot of people take credit for that. And the epidemiologists have noted that there's a correlation lagged by a generation, 20 years, of how much lead we've spewed in the atmosphere and violent crime. And as when we started to take lead out of the atmosphere, as that generation matured, the amount of violent crime went down. Cause and effect, we don't know. Correlation, definitely. So these are the kind of wonderful argument starters that you can get going on. All right, a little bit of physics. It's kind of curious particularly when I talk in public. People struggle with the idea that there are physical laws that operate on the planet that they can't break. Right? My next slide will talk about that. The fact that as creatures of free will, we struggle with this. But there's simply some laws we must obey. And we don't appreciate the importance of a consistent, predictable, natural world. You folks do. You could not forecast the weather if physics was variable, right? If fluid equations, were sometimes, if constants were not constant, if they were allowed to kind of float around from one side to another, you would live in a very, very different world. The example I give is gravity. What if gravity changed by 10, 15, 20, 50%? Be exciting. It would be a total roulette when you got on an airplane, right? And as a matter of fact, airplanes wouldn't exist, obviously, because you couldn't predict how big the wings would have to be or anything like that in order to make this work. The physical principles that run the planet are indeed physical principles, and they operate the same way all the time. And it's really an interesting thought exercise to go down the rabbit hole of why that is, why that's true. You go deeply, for many people, you go deeply into religion right away. For others, you go into, well, this is the only way it could work. There's a lot of interesting thoughts you can get into. But this is one of those things that we don't think about. And when I talk to people about it, they struggle with this. They struggle with it because of this. We like free will, right? So we are creatures of free will, and this collision between creatures of free will and an environment that says, no, this is the way it is, leads to some interesting problems, right? So for example, we knew that if you took coal out of the ground, and coal contained pyrite, iron sulfide, and if you burn that coal, that sulfur in that pyrite is going to produce SO2. SO2, we know when it goes in the atmosphere, reacts with H2O, and that's sulfuric acid. So acid rain was not a concept that should have surprised anybody who understood chemistry, who understood, oxidation. Indeed, acid rain was yet another one of those things that we argued about for 20 or 30 years before we finally did something about it. Right? We knew that acids were going into the atmosphere. They're still going into the atmosphere. We should have been able to figure that one out very, very quickly. And part of the reason why we did not do that is because we don't like limits. We don't like the idea that I should be able to take coal out of the ground, burn it, get energy out of it, and okay, this SO2 thing shouldn't be a problem, right? This is the issue. The SO2 thing is going to be a problem whether you think it's going to be a problem or not. The CO2 thing is going to be a problem whether you think it's going to be a problem or not as well. All right? This is one of my favorite lines. I don't believe in climate change. I've given an entire talk about don't believe in climate change. I think I've talked to you folks about this. Believe is not a word that you can apply to physical principles. And climate change is about physical principles. It's about the vibration of molecules absorbing the Earth's outgoing radiation. They can't do anything else. Those molecules like water vapor, CO2, nitrous oxide, methane, they're going to absorb the energy as it tries to escape the planet and therefore increase the amount of energy in the atmosphere. And energy in the atmosphere, as you folks know, is climate. So you're going to have more evaporation, you're going to have higher temperatures, all the things that go along with that if you put greenhouse gases in the atmosphere. That's not a question of belief. But yet we get this question all the time. Do you believe in climate change? When people ask me that question, I usually back them up and say, can you rephrase the question in a way that I could answer that question? Because I can't answer that particular question. Right? They don't like that, by the way. So a little bit more physics. We live on a water planet. This is another one of those interesting, as creatures of the land, as oxygen-breathing things that live above the water surface, we don't often think so much about the importance of the ocean. And the ocean is extremely important for us in terms of our lives. A lot of the oxygen that's produced are produced by plants that live in the ocean. The ocean controls big climate changes, or even small climate changes. And it controls it because, as you know, water has high heat capacity. So it's really hard to warm the planet up rapidly. It's really hard to cool the planet off rapidly as well because you've got all this water out there. Right? So 90% of the extra heat that we've put into the atmosphere by our greenhouse gases has gone to warm the ocean. Only a small fraction of it has actually gone to warm the atmosphere where we live. If we were fish or if we were mammals that lived in the ocean, we'd have a very different view of this global warming thing. Right? We wouldn't care about those things that live out there on the land surface that have to deal with us. The atmosphere responds to the surface ocean. All right, that's, in other words, things like El Nino and Arctic Oscillation and North Atlantic Oscillation, those things are real because when cold water is coming up to the surface, it air conditions the atmosphere, and when it doesn't happen, the atmosphere warms up faster. And that's basically what's going on. The ocean can have a system in which the surface is relatively calm and doesn't communicate very well with the deep. Under that scenario, you're basically living on a planet with a very thin ocean, and you can warm that planet up pretty rapidly. When you have times in which deep water is circulating up and communicating with the atmosphere, that cools off the atmosphere, and you get the La Niñas, and you get the conditions that change the climate. That's basically, it's not any more complicated than that. What gets complicated is predicting how that ocean is going to circulate. That's fluid dynamics at a big, big level. So this is an example of physics and communication. This is back from the last election cycle. Ted Cruz, in an NPR interview, the scientific evidence doesn't support global warming for the last 18 years of satellite data. and we have satellites that monitor the atmosphere. Satellites have actually measured temperature, showed no significant warming whatsoever. Whether or not that's correct, the point is that if you focus on the atmosphere, you're focusing on the last little bit of the tail of the dog, right? You should be paying attention to the rest of the dog. That's where the teeth are, right? And the ocean makes all the difference here. So what the atmosphere does is interesting, and you can spin tails around it. You can communicate around it. But in the end, it's not the big issue, okay? And this is just an example of that. This is a more recent picture of global temperatures. Now, this is based on land and ocean data. By the way, you see that we are in another, the red thing doesn't work. We're in another shoot-up period here. And this is despite the fact that we haven't had a really decent El Nino to work with. On the other hand, I pulled off the web here somebody's idea that temperature is not changing. Now, and it's just, there's nothing wrong with the data, by the way. It's just that they've chosen to go from 2006 to 2017. So this period in here, although they've not added those points. And they added some interesting other things, like when Al Gore won the Nobel Prize, and the temperatures now. So you can tell stories, and you can communicate in different ways using the same data. And that's an important lesson for you folks, for me as a scientist, for me as a communicator. It's an important lesson for me as well. If this is all you focus on, then fine, all right? But keep in mind this, all right? And also keep in mind physics, right? So that you add greenhouse gas to the atmosphere, you're going to change things. This is the ocean heat content, by the way. And the ocean is doing what the ocean ought to be doing. The ocean's absorbing the energy. The ocean heat content is going up. And there's an upside to that, because as the ocean is slowing down the warming process, it basically buys time for us. We've got 400 parts per million CO2 in the atmosphere. As a paleoclimatologist, I can tell you that 400 parts per million CO2 is not where you want to be. Right? This is a very warm planet. This is a planet that we haven't had for the last 3 to 5 million years. This is a planet with sea level, and we'll talk about that later, a sea level of about 20 to 30 meters higher than today. So if we sit just where we are right now, you can expect things to change. In other words, we've turned the thermostat up. The planet is slow to respond. Right? The downside to this is that the ocean will also take a long time to cool off. So if at some point we say to ourselves, this is not a good idea, I don't like what I'm doing to my kids, however you want to phrase that, however you want to view that, you're not going to be able to reverse that immediately. There's going to be some just as slowly as it started up, it will go slowly back down as well. So we've committed ourselves to a warmer planet already for some period of time. Right? And from a geoengineering point of view, which is an interesting topic these days, it's difficult, very difficult, to air condition the planet back off when the ocean's already warmed up. Okay. Other issues about the fact we live on a water planet, as I just pointed out, it takes a long time for the water to heat up. What I want to focus on here is the intergenerational issues aspect of this. So what we do, what we're doing to the planet right now, our kids, our grandkids, are the ones who have to deal with that. And that's always the case on a water planet. It's what I call the planet of no instant gratification. Right? If you think about it, I mean, you folks know this. If we had a planet in which we had very small patches of water on the surface, not much, but maybe it's all groundwater and we were surviving just fine. At 400 parts per million CO2, we would have a much, much warmer planet already. We'd be another degree, at least, if not more than that, warmer already right now. Right? It would be a planet of more instant gratification. Because of the ocean, it's not. And that creates ethical issues, intergenerational issues that I'll loop back to at the end of my talk. This is my granddaughter, Amelia Louise, and this is, I show this, I never bore of showing this slide. Until one generation is willing to forego short-term gains for the long-term benefit of its children, we won't be able to address climate change. And that's me, that's my quote. But I think I really strongly believe that. Until we can think 50 years, 100 years in advance, we're not going to be able to deal with this problem. Because the planet, physics is saying, no, this is how you're going to have to make decisions. You're going to have to make decisions looking 50 years into the future. And as long as we're not willing to do that, we're not going to be able to deal with this. All right. So a little bit of basics here. You all know this. Global climate is actually, unlike weather, climate is actually much simpler, which is why I became a climate scientist and you folks went into weather forecasting. Because I like it simple. All right. So it's how much energy we get from the sun. We are a sun-driven planet. We have a little bit of energy coming out of the Earth from radioactive decay and friction and things like that, but you would not be able to live on this planet with that amount of energy. The second thing you need to know is how much of that energy is reflected back to outer space. So the Earth has gone through times of high albedo and low albedo. One of the more interesting, from a paleoclimate point of view, times on the planet is when the planet went snowball, where it completely was covered by ice. Getting out of snowball is not an easy thing to do. And there's still a lot of debate about, number one, how you get into snowball, and number two, how you ever get out of snowball. And we know we've been there a couple times. The third thing you need to know about is the amount of greenhouse gases in the atmosphere. And the greenhouse gases are, as you all know, just those gases that have vibrational frequencies in the infrared, which is the energy released or radiated back to outer space by the planet. So if you put those gases into the atmosphere, particularly the lower atmosphere, but it doesn't matter, you will indeed trap energy in the atmosphere, and energy trapping in the atmosphere will lead to roughly 50% of the energy in the atmosphere is expressed as temperature, so you know you're going to warm the planet up. The rest of it evaporates water, so you know it's going to rain more. It's a bunch of things you know right away are going to happen. So the Earth's temperature without greenhouse gases, and we can measure this or we can calculate it, this is 100-year-old information, is about negative 18 degrees, arguably too cold for advanced life. The Earth's temperature that we can measure today with thermometers or with satellites is about plus 15 degrees, which is a much cozier planet. It's areas that are not too hot at the equator, and yes, they're too cold at the pole, but we don't live there. And greenhouse gases are really responsible for that difference. They raise the temperature of the Earth by about 33 degrees, or about 60 degrees Fahrenheit, and arguably, not even arguably, but I think very clearly make it a habitable planet. So this is physics, again, playing out in a relatively simple way, creating a habitable system that we have today. And interestingly, when astrophysicists look out in outer space for habitable planets, they have to take this into account. You can't have a planet that's too close to the sun, because when you add water, which we think is an essential for life, water's our number one greenhouse gas, it will automatically raise the temperature of the planet. And if the temperature of the planet gets too hot, then things don't work. So the too hot, I won't go into the details of that, but too hot is primarily a plant problem. So when it gets too hot, plants respire faster than they can photosynthesize. In other words, they can't just keep up with the amount of internal energy that's required to keep the plant going, which is why plants don't live at plus roughly 40 degrees C or something like that. And again, without plants, you don't have oxygen, you don't have the kind of advanced life that we have. So if we add lots of greenhouse gases to the atmosphere, and there will be more energy in the atmosphere, and by definition, climate will change. This is a physical law limitation. Belief is not really an option on this. This is something that, okay, this is happening. And the adult question is, then what do you do about it? How do you deal with it? Okay, so let me go through some of the aspects of climate change. And hopefully we'll raise some ideas and some comments. It's not always obvious. There are tipping points in the climate system. We know from looking at how the climate systems behaved in the past that it is not a slowly changing thing. So if it was totally controlled by the ocean and by CO2, and by CO2 is controlled by the ocean, by the way, it would always change relatively slowly. It would take 1,000 years or so to go from one climate state to another. As a matter of fact, that doesn't happen. On our planet, we have had temperature changes of 10, 15 degrees Celsius, mean annual temperature changes, in a matter of a few years. And so that has got to be the atmosphere. That's got to be something fundamentally within the system changing very, very rapidly. Crossing those tipping points is not always obvious. The example I give is the canoe on the Niagara River example, which I think I've spoken about before. If you are an explorer coming here to this continent, you don't know it's the Niagara River because no one told you, because you haven't named it. You're cruising down the middle of the Niagara River. It's a fast-flowing river. You make good time. And at some point you hear this roar and you go, well, that doesn't sound good. Maybe I should get over to the side. So there's two possible outcomes. One is you're so much in the fast current you can't make it to the side before you go over the falls, or you've gotten a little more cautious in how you deal with the world and you stayed closer to the shore, knowing that if I don't know what's ahead, I want to be able to be cautious. So it's called the precautionary principle. I want to be able to make it to the shore at any given time. So this person, I think this actually, yeah, I'm not dead yet, but he is, right? He just doesn't know it. The tipping point actually happened sometime up the river when he crossed the point of not being able to make it to shore. That was the real tipping point in the system. The physical tipping point is when he goes over the falls and he's dead. So just a little bit. So abrupt change is a common and natural part of the climate system. We should not expect it to change slowly and change linearly up until the 1990s, which is not that long ago. We thought of climate changes as gradual, forced primarily by the ocean and by sun-earth changes. We know that the forcing is there. It's just the internal variability within the system is something we've appreciated now. We now know, as I said before, that 10 degrees C mean annual temperature changes can occur in a few years, and they have dozens of times. So we have documentation of this. One of the cool things about ice cores, and one of the reasons why, even though I hate the cold, one of the reasons why I go to places like Greenland is that ice cores can still give you year-by-year temperature changes 20,000, 30,000 years ago. You can still see that. So it's a really nice way to... Yes, Jennifer.
I'd like you to speak to something that we talked about yesterday and these abrupt changes and how it can happen in a very short period of time. We talked about, and not that there's any research on this, or maybe there is, but the notion that if you lose the ice at the poles and you lose that constant cold, which is where we see the polar vortex, and you lose that constant in the computer modeling, what happens to our jet stream and what happens to the weather patterns once you lose that constant? And maybe you can just speak to the climate side of it, obviously.
Well, actually, the next 4 or 5 slides address that. So your timing is perfect. All right? So there are abrupt... I know. There are abrupt changes are not something that's just happened in the past and will never happen again. We're in the middle of an abrupt change right now. And that abrupt change is the disappearance of summer sea ice in the Arctic. This is happening much faster than we originally anticipated. This impacts Arctic ecosystems. It impacts changes to shipping, coastal erosion. It impacts, as you know, how cold the Arctic gets, which impacts the jet stream, which impacts weather down here. So we'll spend the next few slides talking about this. This is just I've shown this before. I never grow tired of showing this. This is a NASA animation showing sea ice in the Arctic going back into the 1980s up until pretty close to today. What's important here is that the white ice is thicker ice. So the way that the Arctic functioned for the last 10,000 years was that it got cold enough that big thick ice, 4 or 5 meter thick ice, formed. And it's always being flushed, by the way, out here on the east coast of Greenland. That's just the way the ocean circulates and the way the atmosphere circulates. But the amount that was flushed out was equal to an amount that was reformed here within the Arctic over the last 10,000 years. What's changed is that the amount that's flushed out is now more than the amount which is reformed. And so the Arctic, rather than being, and you can see changes here, the white stuff going away, rather than being an ocean that's resilient, or a sea ice pack resilient to change, because it's 4 or 5 meter thick ice, it is now an ice pack which is not resilient to change. So this is, what are we up to, 2013? We'll get there. But you see, interestingly, we talk a lot about the Northwest Passage. We heard about that on Tuesday. That's probably one of the last places where you're going to get rid of all the big ice. But what has happened now is that you've got, while we have sea ice in the wintertime up here, it is thin. It's maybe a half meter to a meter thick. Right? That ice can go away any given summer when we get the right conditions. If we get the right conditions that flushes ice out, if we get a lot of warmth up there, then you change. And you folks know the difference between white ice and blue ocean from a summertime albedo point of view is huge, and also from a wintertime warming point of view. This is the feedback that we think is really important, that when you lose the winter sea ice, you can keep the atmosphere much warmer because the ocean is sitting there at a few degrees or even warmer than that. Yeah, Joe.
Jim, what do you tell the people? Because back in the Inconvenient Truth days, they did give a prediction that sea ice would be gone, and it should have been gone already. And people kind of rub your face in that all the time. But then we also have scientists like you who are saying it's disappearing quicker than we thought.
Yeah.
Isn't that kind of a quandary? What if you got that? Tell me what to say to them.
Yeah, actually, if you look at the ice prediction models that we had back in the 80s and into the 90s, they all predicted it would take longer for the ice to go away. I don't have that slide, but all of those models are up here in terms of time going by. What actually happened is it went away faster. It's going away faster. Now, in the end, it doesn't really matter, right? So just because somebody like me makes a bad prediction doesn't mean that you should all go. Yeah, no. Doesn't mean you should ignore. You folks live that. If your weather prediction doesn't pan out, it doesn't mean that your viewers are going to just, all abandon you and say, we don't know anything about weather. So, I'm giving up. I shall not watch the weather forecast ever again. Maybe my dad said that, but there's the vast majority of human beings recognize that, okay, sometimes you get it right, sometimes you get it wrong. But in general, these 3 to 5 day forecasts rock, right? They are really good. They don't suck. So this is the, again, I wouldn't get too tied up in the prediction didn't come true kind of thing, because that's a rabbit hole you don't want to go down.
They shove me in there all the time.
Yeah. So let's take a look at what this means for some of the various, and I think we've talked about this before. There are some things that are predictable, some things that are less predictable. So let's stick with the predictable stuff for the moment. Atmospheric circulation cells move north. So as you warm up the planet, the Hadley cell, the other big circulation cells expand because there's more energy in there. So you get air rising at the equator, moving north. So those cells expand, and where they sink, you have dry areas. You have the Sahara, you have New Mexico, etc. So one of the things that all the models seem to agree on is that those cells expand. And so New Mexico becomes the new Colorado, which for those of us in Colorado is a pretty uncomfortable thought, because if you go down to New Mexico, it's dry, right? It's desert. And here we have grasslands at least. And the future of those is sketchy. We know, for example, that sand dunes, dry sand dunes, were active in western Nebraska, western Kansas, about 4,000 or 5,000 years ago, when it was drier, when it was warmer. And so that's, we know that change can happen. Matt?
Wouldn't it be Colorado is the new New Mexico?
Oh, did I get that wrong? New Mexico is, well, yeah, no, you're right.
Bingo.
Bingo!
I put that in there on purpose.
Colorado's going to act like New Mexico.
Yes.
That's what you're saying.
New Mexico is going to be the new, Colorado is going to be the new New Mexico.
Had too many news together. He couldn't.
Yeah. And also decreasing the equator to pole temperature difference has consequences, as we've talked about at this conference in the past, and this is a really interesting ongoing debate right now. As you increase Arctic temperatures and therefore decrease the mid-latitude to Arctic temperature gradient, you change the amount of energy that can go into the jet stream. And as the jet stream becomes less energetic, like all streams, it slows down and it becomes loopier. Those are like me. So the importance of that is still a hot topic of debate among climate scientists. But I would say that the observations now support this, that you do see loopier jets. You see slower moving storms because the jet itself is moving more slowly. This means more big snowfalls, more big rains. We've already seen in the eastern United States, for example, about a 70% increase in big rainfalls, and you can define that. Cold air is less bottled up. The outbreaks, we think, can go at least as far as they used to go, if not farther as time goes by. As I said, the storms move more slowly as the jet becomes wavier. So Jennifer, back to your question, this is we think, a natural outcome of a warmer Arctic. Okay.
So Jim?
Yeah.
So that your final point on that graph becomes a pretty big communication problem.
Yeah.
Because we're getting cold air outbreaks going farther south, and that's a result of global warming.
Yeah.
And so we all get it in this room, but to the public, that's not a very convincing argument.
No, and it's not an easy argument to explain. It's not easy to explain, how. But that is if you look at how the planet functions. What?
I don't have the mic. The answer is to show those people a hemispheric departure from average temperature. And it tells nobody can hear you.
As soon as I use the words hemispheric departure, I've lost them. Jim.
Yeah, but while we have any particular cold outbreak
Yeah.
is a function, that's weather.
Yep.
So what we want to do is we want to take a look at the climatological mean. Are more of these coming in? How is it changing the statistics? That's the nature of climate change, and that's where a lot of people get confused. They confuse weather with climate.
Yeah.
Zoom out. It's not just Columbia.
I thought the world revolves around Columbia.
Yeah, go ahead.
Thank you, Frank Billingsley from Houston. So we just had 19 degrees in Houston.
Yeah.
The coldest we've had in 22 years.
Yep.
16 in 1996. When I first got there in 1989, we had a huge Arctic outbreak. We had 7 degrees on December 22nd, followed by 11 degrees the next day and 13 degrees the next day. So what I take from your cold air is less bottled up and outbreaks go farther is that the outbreaks go farther, but the air's not as cold as it used to be.
Excellent.
No, I don't even know that that's the case. What I tell people is there's less cold to go around. You're still going to have cold, and
But
with
it's-
these higher amplitude jet stream reacting to the warmer climate, they're going to.
But my example didn't use the word amplitude. That's the thing. I can show you 7, 11, 13 in 1989, and then it got to 19 the other day, but it didn't get to 7. So why didn't it get to 7?
No, so this is an important, and it adds to the complexity that Matt is pointing out here, that yes, because of greenhouse gases in the Arctic are trapping outgoing energy, the Arctic is not getting as cold as it used to get. It used to get, negative 40s, negative 50s, negative 60s were not uncommon in the Arctic. They're becoming less and less common because you can't build up that really, really cold air. So the cold air sloshes down, but it's not as cold as it used to be.
So when on Facebook they say, well, here comes global warming, it's 19 degrees, you say, yeah, but you know what, it was 7 30 years ago.
Exactly, here comes global warming. So it's hard to tell people that 19 is global warming. We had this discussion, Kent and I had this discussion with St. Louis the other day. It's hard to express that 19 is good, but indeed that's the case. If you look back at the 1950s and 1960s, and even the earlier, back into the early 1900s, the incidence of these cold air outbreaks was much, much higher, about 5 to 10 times more often, but not as cold today as it was in the past.
That's a really good point. Good point.
Yeah.
I have one quick question.
Yeah.
Phil Klotzbach, Colorado State. Just wondering, with the whole blockiness kind of question, I always kind of like to say, well, let's look at like climate indices and see the trends, because if physically it makes a lot of sense. But if you look at, say, like the Arctic Oscillation, you plot just a linear trend line since 1950, there's no trend, no significant trend. If anything, it's slightly up, which would mean more zonal flow. So I'm just trying to figure out, like, is it just that that's not a good metric to be looking at, or is it just not the right? I'm just trying to figure out kind of how to.
No, I think, and as I tried to say earlier, this is an area of a lot of debate, a lot of contention. As a matter of fact, I would encourage you to invite people to this conference to talk about this particular issue, because it is an argument out there in the meteorological community, in the climatological community. Right? How do you measure it? You know, from a simple point of view, you can think, yes, if you got less energy in the system that drives the jet stream, then the jet stream is going to get slower and wavier. Right? That makes some simple physical sense. But measuring that and knowing what that means from a climatological or a weather point of view is a much more interesting conversation that folks in this room would really enjoy. Yeah?
I was just going to say, and the communication part of this obviously is kind of difficult, but one of the things, I mean, we all cringed when the polar vortex became like this catchphrase, but it was a great learning experience for the public because you could explain to them the reason we got cold was because of a weakening of the polar vortex. And sometimes you see these maps floating around, we get these East Coast cold outbreaks, and the way it's colder here than Alaska. That's another way to show, hey, look, it's warming up there, and it's actually causing that cold air to come south. So those things are they're like clickbaity, but they're actually pretty good tools to teach the public about what's going on up in the Arctic is having huge implications.
No, I agree with that. I think these issues that we're talking about are very good discussion, leaping off points to educate folks about how the planet functions. And it's, you know, one of the things as an educator that I rail about is that we don't have an educated citizenry for the most part. Right? They don't understand even some of the simplest issues, and
can't read a map.
Yeah, can't read a map. So this is something, and this is something we can fix. You know, we can educate people. We can have 15 minutes. Oh, I'm screwed. Okay.
I'll shut up.
All right. So I'm going to blast through. Matter of fact, I might just skip the end of the talk, but I just want to point out that the Arctic is changing. Something that we don't think about because we don't live there, but it does have, as we pointed out, impact on our weather. But it also has geopolitical impact. We can now sail ships up here. We talked about this the other day, the famous Northwest Passage. Most of that traffic is now going around the Russian side, and the Russians are charging money for this. The Russians have a very aggressive policy of expanding into the Arctic. And while we're ignoring the Arctic for the most part, we're still arguing about whether or not we ought to replace icebreakers from 30 years ago. The Russians are very strongly expanding into this area. And I'm not demonizing the Russians, I'm just saying that there are other countries who see this as opportunity. Right? We're going to have, and we've already starting to see some folks build nice little summer homes up here in the Arctic. Right? If I lived in the Arctic, I would view this with, oh my God, what's about to happen here? Because the last time there was a big land grab, happened to be here in North America, it didn't go well for the natives. Right? Did not go well at all for the natives. And so the folks who live up in the Arctic are nervous about how this is going to play out. All right, some more simple physics here. More rain, less snow follows from a warmer planet, especially in the spring and the fall. One of the interesting things from a skiing point of view, since we're here skiing, is that here in Colorado, we've begun to lose Thanksgiving as a ski holiday, as a dependable ski holiday. Occasionally it happens, but for the most part it doesn't. That's big money.
In the East, it used to be Thanksgiving to Christmas. Sometimes we lose Christmas.
Yeah, yep. Shorter ski seasons, particularly at lower elevations. I don't know the total dollar amount for skiing, but in Colorado alone, it's a $5 billion business. Right? So that's huge for the economy of this state. And snow is a free reservoir globally. Right? That is shrinking. And if we want to keep the fresh water available to us, we're going to have to start building more dams. And that, again, is an interesting sociological debate. It's an interesting public debate. Here in Colorado, we're expanding one of our reservoirs, just expanding it. And they calculated how many trees it would take out. It was hundreds of thousands of trees. But that alone is headline news, and people get really bent out of shape. Their shorts are way up their butts, on this one. So It is a hot button issue. And yet, we need the water. And so how are we going to deal with this? So there's some interesting combat that goes on towards a sustainable future, depending on what side you come down on. A fire-filled future, we just talked about this, but hotter summers mean drier conditions. They mean more of evapotranspiration. Everything dries out more. Warmer air also means greater potential for large rainfalls. And so what we've seen, and we can look at the tree ring record and other records, you get bursts of vegetation growth, which then create problems for fire. And so it's a boom-bust cycle, if you will, from a fire point of view. These are really part of the recipe for more wildfires. One of the reasons I asked you the question. And yes, I mean, we're thinking about these things. We know that wildfires are going to get more and more problematic as time goes by. And then you throw in the fact that people are building homes in the middle of forests now and creating additional problems. Ecosystems do matter. This is a local picture of what the pine bark beetle did. Here in the Intermountain, or the Mountain West, vacation and second homes drive most of the main economies here in the West, between Colorado and California. So it's second homes in Idaho, it's second homes in Colorado, it's second homes in Montana that are driving mountain economies for the most part. And as the ecosystems change, as the beauty changes, then values change. The impacts are not all local. What happens elsewhere will matter to everyone's economy. We're all tied together. Food costs or food security is a main topic of papers and conversation among scientists who look at sustainability. It doesn't penetrate out beyond the scientific community very much these days. It's not something you hear about in the press very often, but food security is a term that we talk about quite a bit. And we will all pay a lot for sea level rise. All right? We know this, that you, and I'll just show you at least one slide. So just very quickly, I'm not going to have time to go through all the stuff about sea level, but I just want to show you a couple of slides, a couple of plots here. This is global mean temperature here and sea level, and I make this point, but this is one of those really hard points for people to digest. All right? The dynamic range of temperature change is about 6 degrees colder going back 20,000 years ago, about 4 degrees warmer going back 40 million years ago. Right? So it's about 10 degrees C dynamic range of temperature change. Over that same temperature change, you go from 120 meters lower to about 80 meters higher in sea level. That's 200 meters of sea level change. All right? 200 meters of sea level change, 10 degrees C of temperature change. You can do the math. A degree C, if it was linear, it's not quite, I'll show you, is about 20 meters. Right? 20 meters, for your viewing areas, folks, yeah, right, you're toast at that point, right? So this is one of the things that we've learned over the last 15 to 20 years, that sea level on our planet is not level. It's been level for 10,000 years by really some interesting quirks. If you look at the history of sea level, it doesn't remain that level for that long very often. And it can change, and it can change by very large amounts, right? So coasts or toasts. Where will the new beach be? So let me just, this is another, and I apologize, this plot gets a little bit more in the weeds, but there's a couple really interesting things on here. One is, so this is now the relative sea level. It's plotted versus atmospheric CO2, so as the driving function is CO2 here. This is the glacial, where your CO2 levels drop to 200 parts per million. You get a lot of sea ice, or a lot of land ice forming, takes water out of the ocean. Note that, and there's a lot of scatter on here, but in general, if you go from about 300 parts per million to maybe 700 parts per million, you're looking at sea levels that are about 14 meters higher than today on average. Right? And I don't have time to go into it, but there's a good reason why 14 meters. But what's even more interesting on this, I think, is that somewhere around 700-800 parts per million, it's a warm enough planet that there is no Antarctica and there is no Greenland. And all that land ice gets dumped into the ocean, and you end up with something 70 to 80 meters higher. Right? We're at 400 today, and we could hit 700-800 parts per million. Now, as I pointed out, because the ocean takes a long time to warm up, when you get 700-800 parts per million, when you turn the thermostat up that high, You won't get 70 meters sea level right away, but you will get it eventually. And whether or not you can turn that around, whether or not you can say, all right, I'm going to suck that CO2 out of the atmosphere, that becomes a really important question. And it's a question we can't answer yet as climatologists. Right? So again, where's the tipping point in the system? All right, now I'm just going to finish up because this is just some nice pictures of sea level going away. Oh, by the way, here's a nice little communication point. I think I've shown you this before, but this is one of my favorite slides. USGS, this is a screenshot off of dogsports.com, which is the Georgia football fan website. And they say here, the USGS predicts that if the ice caps were to melt completely, sea level would rise by approximately 80 meters. That's right. Congratulations. If we can get the polar ice caps to melt only halfway, sea level will rise by 40 meters. And the face of the Earth will change forever. I have family down here. I have friends down here. I can tell you that we don't often talk about climate change because we get off in the weeds pretty quickly. But if climate change means that Gainesville, Florida is underwater, this is a good thing, right? I'm willing to accept the physical principles of sea level rise if it means the end of Gator football, right? So this is, no. But it's an interesting way to change to enter the conversation, right? So if you enter the conversation by saying sea level's rising, you're not going to get very far with a lot of these folks. If you enter the conversation by saying, hey, did you know that if sea level rises enough, that could be the end of Florida Gator football, they'll go, whoa, okay, let's have that conversation. All right, so I'm going to leave you, I always leave you with these three thoughts. I'll continue to do this. We already talked about this. Thought number one, show the kids some love. You live on a water planet. If you don't pay attention to the next 50 years, you're going to never solve the problem. So think about your kids. Think about your kids, all right? Thought number two, show the poorest of the world some love. We've got 2 billion people. If they go into the same kind of fossil fuel consumption or same kind of energy consumption that we are, same kind of water consumption that we have today, be very, very, very challenging, all right? They have got to be at a high enough economic level that they care about the planet, that planet health, that the collective health, if you will, is something on their radar screen. That's got to be something that they think about. And right now, they are just thinking about food for the next day. They're thinking about shelter for the next day. They're not thinking about sustainability, right? Thought number three, it's time to end male dominance, right? We live in a world in which we've got to deal with population increase. And the number one way to deal with population increase is to empower women politically and economically, right? Demographers tell us this over and over and over again until they're blue in the face, and we go, how are we going to deal with population? Well, yeah, you can deal with population. You deal with it by changing the power dynamic that has existed for thousands of years between men and women. And wow, don't we live in interesting times, right? It is about time to end male dominance, and I believe that's about what we're seeing these days. All right, I'll stop there and take questions. Ellen, you got your hand up?
Yep.
And then off we go.
Dr. Ellen Prager, I'm with Earth to Ocean, Inc., and one question for me and one from Facebook. So, Jim, would it be fair to say in the earlier question about the predictions early on about the Arctic sea ice that one of the reasons they weren't exactly correct is also because our technology has advanced so far that we're learning so much, and the data pool is so much better now than when a lot of those predictions were made?
Yeah, as a matter of fact, I would go further, and I would say that the whole field of climatology has advanced tremendously over the last 20 years. And it's kind of, I wish, if you had to rewrite history, you would hope that we could have gotten climatology right in the early 1900s or maybe late 1800s. So we'd be ready for when the CO2 levels start to shoot up and we go, okay, we got all this figured out. But that's not the way it happened. This is one of these things where, we invented nuclear weapons, and then we had to invent a way that we were responsible around nuclear weapons. We've changed the climate. Now we've got to figure out how to deal with it.
Right, but I think if you all get that question about what about the earlier predictions, I think one of the answers to that is about how much technology has advanced and how much more we know now than when those predictions were made.
Yeah, no, it's
Right.
very, very we are changing rapidly.
So
you know, as I said, when I was in graduate school, we didn't know about sea level being that dynamic.
Right. So the second question comes from Mike Collignon. I don't know if any of you know him. And I think this is a great question. It says, do we ditch the term global warming and just use climate change?
Oh. You know, we debate that all the time. Semantics, it's a little bit semantics to me, but it's important semantics. I think global warming does indeed convey something important, which is, number one, it's the globe, and number two, it's getting warmer.
So I will tell you, from my field in oceanography, they say they like climate change because they're saying it includes other impacts other than just warming of the globe, like ocean acidification, sea level rise. And so in my field, at least, they're using that as a much broader topic.
Yeah, no, I get that. I think from a scientist point, I don't talk about global warming when I give scientific talks. I talk about climate change. But when I talk to the public, I talk about global warming. So maybe it's audience oriented. Jim?
Jim Gandy at Columbia, South Carolina. You know, you were talking about the importance of the amount of heat that's going into the oceans. And I've been looking at this problem for some time. And there was a paper, and I brought it up on my iPad here, that was published in Geophysical Research Letters back in 2012, which analyzed the amount of heat, the change in the heat that gone into the ocean from 1955 to 2010. I just wanted to throw this out there because this was a result that I kind of took to heart. If the heat were instantly transferred to the lower 10 kilometers of the global atmosphere, it would result in a volume mean warming of this atmosphere layer by approximately 36 degrees C, which I think...
I remember that.
Which is 65 degrees Fahrenheit. So just in that time period, you doubled global warming. I mean, doubled the greenhouse effect. Yeah. And that's just the benefit that the ocean is giving us right now by absorbing so much heat.
The ocean benefits us in many ways, including it absorbs about a quarter of the CO2 we put in the atmosphere. But as I said, the downside to that, Jim, is that when you try to turn it around and you say to yourself, well, maybe this warming thing is not such a good idea, the ocean's going to still be warm, and it's going to continue to keep the atmosphere warm for quite some time into the future. Yeah.
Doug Cameron from WRC, looking at the oceans and the balance that the oceans and the atmosphere have to have. It seems like when you look at the trend with temperatures, you get a little bit of a period where that balance comes into place, and then it's almost like the oceans say, oh, can't take any more heat, into the atmosphere it goes, and then that balance is formed again at a higher plateau.
Right.
And you continue to see that. Is that something where eventually that balance is going to be so out of whack that we do continue on that much faster transgression?
In general, yes. I mean, because the ocean continues to absorb heat and it keeps trying to warm the atmosphere up, it'll eventually drive the atmosphere up. So the ocean's going to give you, if you think about it this way, the ocean gives you sort of the base notes. It's going to just keep going up. Because the ocean has circulation patterns from surface to deep, where you can bring colder water up to the surface and therefore keep the planet from warming up so much, the high treble notes are the ocean circulation. So that's what's keeping you not warming up for some period of time. But then, if the ocean becomes more stable, it really shoots up. I mean, if you look at, I can't go backwards. Can I go backwards? I go backwards.
That's my exact question.
I can go backwards.
While he's looking, we're into the 5-minute, we have a 5-minute break period, so we're just going to keep going because the conversation is good, so keep going.
Yeah, so for example, you see on here, I don't have it labeled on here. Actually, they didn't label on this particular one that I stole from NASA GISS, but you can see the El Niños and La Niñas on here. This is, this recent warming is pretty impressive, given the fact that we don't have as stable an ocean surface as typically you have when you're able to do, these kind of rapid increases in temperature. Matt.
So, Matt Safino, Portland. So 2 questions, Jim. Can you elaborate a little bit on what the Russians are doing to take advantage of the Arctic? And would you, or does anybody ascribe or differentiate the natural variability versus climate change costs of some of our recent extreme weather events, be it the hurricanes or the wildfires in California?
So, excuse me. To your second question, this is something that I think happens. It's a hot topic of research. Can you ascribe either individual events or clusters of events to climate change? Somebody got some water?
That's yours.
Is that mine? Cool beans.
Wait, that's mine. No, go ahead.
Oh.
I'm serious. Go ahead.
Craig Cooties. I think that that's really an important thing to do. But how you approach it is interesting. With 400 ppm CO2 in the atmosphere, you could argue that every climate event out there, every weather event out there, has a fingerprint of climate change already in it. It must, right? With 400 ppm CO2, and it used to be 280, we must have more energy in the atmosphere. And so every event that happens today would have happened differently 50 years ago. All right, so that's one argument. There are other arguments you can make. What was it? Oh, Russia. So the Russians are very aggressively moving from an oil and gas point of view into the Arctic, and they're moving from an expansion point. Russia's got a huge amount of land that is currently not terribly occupiable because of cold, because it's frozen, permafrost, etc. They are, global warming to the Russians is not a bad thing. It is a wonderful thing to them.
A lot of farmland. So a lot of it's land-based of what they're doing.
Yeah, a lot of it land-based, but also coastal, right around the coast. They've got shallow waters off their coast that they can go out and do oil and gas exploration. Yeah, Craig.
Hi, Craig Setzer from Miami, 5 feet above sea level, also known as the canary in the coal mine. So one of your first slides was the world has changed, and you had China at 5.9% and the U.S. going down.
Yeah.
Minus 3.7. And I almost feel like while everything you're saying is compelling and very thought-provoking and even action-provoking, I feel like I've got the house in the neighborhood that's doing the right thing, but across the street, he's letting everything go crazy, which is affecting my house too. What do we do with that?
You mean how do we get our neighbors to get on board? Or?
Yeah.
I think education. I wish I had a good answer to that. And as an educator, I maybe a couple times a month I still go out and lecture in public. I move the needle a tiny, tiny, tiny amount. Right? You folks have much larger audiences. You can move the needle, I think, a little bit more. But we all know that there's only so much needle moving you can do. Really what we need is we need leadership from the top. We need people willing to act down, at our level. And so you got to combine that education of the masses, if you will, so that when a leader comes along who says, yes, we need to do something about this, they're willing to follow. We're not at that situation right now.
Jim,
yeah.
Paul Goodlow, Weather Channel. Looking at that graphic, up until about 1987, U.S. and the EU in lockstep. Then EU drops off.
Right.
And the U.S. keeps going. What caused that drop off? And they continually try to, I guess it's trending lower, and the U.S. over the last 10 years maybe.
So there's several things that are going on here. In general, that break is OPEC, the impact of OPEC. So when OPEC raised gas prices over a short period of time, countries had different responses to that. Many European countries who do not have oil and gas and felt very vulnerable to the supplies of oil and gas went down a different pathway from an energy point of view. Denmark became a leader in wind energy, for example. France went whole hog in nuclear. There's a whole bunch of different ways in which they responded to that. We responded in a let's buy more oil way, right? Although we did have a momentary hiccup there. By the way, this is the impact of directional drilling and fracking has had on our carbon footprint. We produce more natural gas, less coal, and that has brought our numbers down.
So oil was more expensive in Europe, and that caused the...
Oil's expensive everywhere, but what Europe said was, we don't want to be vulnerable. We don't want to be in a situation where if Saudi Arabia or the Middle East or, oil is found in some pretty interesting places, right? So we don't want to be in a position where we have to be, we have to change our international policies in order to meet our energy needs. We took a different path.
Joe Murgo from WTAJ in Altoona, and before I get to my question, that was a very interesting fact because oil now has gotten that much cheaper again. I'm in the heart of fracking country in Pennsylvania, and it's getting decimated. They're closing up because oil is so much cheaper, people are turning away from it, and that's a scary thing because that may actually turn the corner again.
It probably will flatten out there.
Wow.
The big change that occurred was the ability to drill down and steer the bit along formations, and when that happened, it was no longer fracking in a small area, it was fracking in large areas.
Very important. And there was a great talk, and I don't know if you heard of this at AMS Austin, where they ran the mathematics behind Harvey. And by the Gulf being that much warmer than average, took the extra temperature, they were able to calculate the extra energy removed through evaporation, and it actually matched what some of the rainfall was. They were able to transfer that to the rainfall. But these major hurricanes, they're the oceans burping out the heat, aren't they?
Well, yeah, the ocean's definitely warmer. So, and you know this, the hurricanes are delicate creatures in some ways. But they need fuel, and that fuel is warm oceans. And as the oceans, and particularly the Gulf, has gotten warmer, it's been able to fuel larger hurricanes. Doesn't necessarily mean it'll fuel more hurricanes, because you also need steering winds to be behaving themselves and a whole bunch of other things. But you know, the concept of bigger storms in general in a warmer world is one that makes a lot of sense from simple physics.
Howard Bernstein, WSA Washington. Jim, I was at a conference in the spring, and a lot of folks were complaining, like we talked about it earlier, that you try to teach somebody something and they just don't get it, you know, and they're complaining about how much time and effort it is to try to educate somebody. And I just said, hey, it's going to be innovation. It's going to be your wallet. When you convince the guy who may not understand it, but you come up with something that makes it cheaper for him to keep his truck running, you know. So I'm of the belief that maybe we need more energy because we can't educate everybody. And we've got the 2 billion in poverty across the world that you said, that it's going to be innovation and technology that turns the corner for this, as opposed to widespread education and volunteerism.
You know, I think this is a really fascinating topic. And if you folks have been immersed in this for a long time, because you've had to go out to the public with your forecasts and with things that you know about weather, and you know about severe weather and hurricanes, et cetera. And you know that the level of education out there is critical to their willingness to accept what you're saying and act on what you're saying. And it must be incredibly frustrating, you know, when you get the same kind of bad reaction because people haven't learned, you know what they still don't understand, you know, the basic ideas behind hurricanes, et cetera. So, to me, Howard, I would love to have a world population that understood how our planet functioned. I mean, we live on a common planet, and I know the basics of how my heating and air conditioning system function because I like my house, and because I want my house to continue to function. I think we should all have some simple understanding of the air conditioning and heating of our planet, and we don't. And that is frustrating. And I wish it was different, but it ain't. And on that wonderful point, one more?
One more question from Steve, and then we'll jump into the next presentation. It's terrific discussion.
Steve Eagle from NBC in West Palm. That you actually kind of answered my question. And my question is for the entire room in this world of consultants and 230 for weather. Has anyone found anything creative to pass along the climate change, you know, story? Because I feel very limited in what I can do because, you know, my boss wants the weather forecast.
You know, one of the things, this is Dave Jones from Storm Center, one of the things you might want to consider is, you know, and it's the reason for the Weather and Climate Summit in the first place, is to build these relationships with scientists, right? So Jim White is no stranger. Call him up. Set up an interview.
Actually, I'm pretty strange.
Interview him live. Well, he's somewhat strange, but he has really good facts. Make a connection with the speakers that are here. That's why we have the Weather and Climate Summit. You have questions on fire weather. Call Heath Hockenberry. talk to the National Weather Service. That's why we bring everybody together, and it takes a little bit of the pressure off you to have to explain what's going on, because you're tapping into a subject matter expert who knows all about it, and maybe you'll develop it into a series for the book or something like that. So I think we're going to have to move on, even though this was awesome. And sorry, Jim, we usually give you 90 minutes. We had 3 presentations this year.
All right, I'm out of here.
This is terrific.
All right.
Thanks very much.